Okay, so we just talked about just recapitulating, like we just saw how linear regression can be written, the best fit line W0 plus W1x, that you can write as a linear combination. Okay, so same thing I told you that regression line you can write is a linear combination of fxi's. Okay, so therefore even if fxi's are non-linear, still it is a linear regression. Okay, so basically it depends on these alpha i's, whether you call it linear or non-linear. And most importantly, I gave you one example, W0 plus W1x plus W2x square is still a linear regression, but that is a kind of a polynomial and is used to fit polynomial data. If you have data sets and the points look like this, then if you fit a straight line is not an ideal choice. Because if you fit a straight line, of course, you're missing out a lot of data points. Instead of that, you can just draw a polynomial line, polynomial curve. Okay, how you just use the polynomial curve from W0 plus W1x plus W2x square. Okay, so this is the fitting of some polynomial. Okay, fine. So regression is linear. Regression is linear as long as the normal equations which involve W0, W1, W2, and so on are linear, even though we are fitting y and x through a non-linear relationship. What the idea? When to call linear and when to call non-linear. Important. Okay. So these can be some good interview questions. Okay. He might give you this x square and xn some power and ask you whether it is a non-linear regression or linear regression. Don't see xm and write non-linear regression. Okay. Okay. So in least square regressions, the estimation function is a linear combination of basis function fix, this fxi. Okay, y is a linear combination of f of xi. You got that. What is y? Y is an estimation function. Y is an estimation function. Like, given the independent variable, you are estimating what is the value at xi. Okay, so that is an estimation function. So therefore, you can write estimation function y cap as summation of alpha I fix I equals to 1 to n. Okay, fine. Alpha I are referred to as parameters of the estimation function. Parameters of the estimation function. And what are fix? Fix are the basis functions. Basis functions. What does it mean by basis functions? What are basis functions? What are basis functions, Shabna? Come here. But please. There. Okay. Fix are basis function. What does it mean? Fix are basis function. What does it mean? What does it mean? Fix are basis functions. What does it mean? It means f1x, f2x, and so on, fnx, whatever, are linearly independent from each other. Are linearly independent. I think we discussed this linearly dependence in the last semester. Computational science. Linear algebra, we discussed, right? So therefore, the function should be like that. The function should be like that. Okay. Okay. Fine. Okay. Now we are slowly advancing towards linear algebra. Which can give you a motivation of pseudo inverse. Okay, useful in regression, and also Python has a command like pinv pseudo inverse. If you give the, it will give you what is the set of vectors. So the idea is simple. We are not working in linear regression right now. Okay, we are working in something more, something more. What is that something more? Okay, what is the idea? Y cap is equal to W naught plus W1x. Our aim was to find what is W naught, what is W1. Similarly, in this example, we W naught W1 in a vector form. And our job is to find that vector in linear algebraic concept. Of course, you won't have W naught W1, rather you will have a lot of unknowns. That's what you have to deal with matrices. Okay, fine. So we'll see this at each exercise. At each exercise, can we write this? Can we enumerate this function at each exercise? Enumerate this. Enumerate the data at each exercise. If you do that, what you get? Anyone? So y hat at x1 should be should be alpha 1 f1 x, yes, plus alpha 2 f2 x1 plus alpha n okay. What is y cap at x2? Alpha 1 f1 at alpha 2 f2 at x2. Okay, so on till fine. So far fine. So on do till suppose you have xm points. Suppose you have xm points. Okay, it is not necessary that you have n number of points. The number of points and the number of points in the data set and the number of basis functions can differ. Why they should have a correlation? So suppose I have m number of data points, but n number of basis function and n number of alpha is. Totally generally I am writing. You understand, right? Y cap at xm. What I should write? Alpha 1, yes, plus so on. Yeah. Then yes. So I hope you are getting it. Whatever I'm trying to do. You have enumerated all this in terms of this. Now the idea is, can we use our last semester to do something here? What is our aim? Our aim is to find alpha is. Our aim is to find alpha i's. F1 at x1, F1 at x2, y cap, and all this you know. All this is known to us. Now, can we write it as ax equal to b kind of format? How can we write? Anyone? What should be the plan? What should be the plan? If okay, there are n unknowns, alpha 1, alpha 2 up to alpha n, and of course we cannot solve it using hand. Therefore, we learned in the last semester ax equal to b using lot of Gauss-Seidel other Gauss elimination methods. Now, can we write this in terms of ax equal to b? How? What should be the plan? The plan should be like this. If you have a problem, the plan should be like this. That how about I can gather all these y caps into a matrix. Okay. And there is a matrix multiplication alpha 1, alpha 2, alpha n. Okay. And it is being multiplied by f1, x1, f2, x1, f2, x1. Okay. And fn, x1. Okay. So on. Okay. Now can we write it in matrix format? How we can write? Tell me. I'm going to next slide. So our aim is to write y cap is a beta. Y cap is a beta. Okay. So what is a and what is beta? Anyone? What should be y cap? y cap at x1, so on at y cap at ish. Good. Then A, how it should look like? Is it a column vector? Column vector. Okay, you tell. Alpha, how? Alpha 1, alpha n. Okay. What is beta? F2 of so on till Fn at xm, x1. Okay. Then like this. Then till you multiply. So this is 1 cross n. This is m cross yeah. I'm writing whatever you are saying. You have to be tell what is the size of beta? M rows x1, x2 up to xm. How many columns you have? N. Okay. So now what I should do? I should write A not as a row vector but as a column vector. B matrix should be like. So then what change it will be? N cross M. Yes. So now you know the mistake. Okay. So actually, so what it should be? A equals to alpha 1, alpha 2, so on up to alpha n. What should be beta? Beta should be f1 x1, then f1 x2, then f1 xm. Fine. Then f2 x1. Okay. So on till so n rows, m columns. Here n rows, one column. Two vector. Okay. Correct now. This is 1 cross n, this is 1 cross n cross m. So A into beta should result into cross m vector. Now is it 1 cross m vector on the left? Oh. At least he is trying. No, we have to write into A into beta. Because then it will be easier a bit. How we can do it? B and beta into A, you won't have problem. But why we write always Ax equal to B? Why not Xa equal to B? No, but simple enough, right? Why we are not getting this? Of course, you can just, so there is some discrepancy with the row and column vectors only. Oh, that also you can do. But I don't know. I think we can change, but it might affect us when we are taking this transpose and all. Is it so? Okay. How about let us see y cap you treat as a column vector. Suppose y cap you treat it as a column vector. Okay. Then what you have? Then what other changes can we make? I'm not understanding. This is being multiplied by this. 1 cross m, m cross m, 1 cross m should be there. But then what is the use of also you take as a column vector? Beta, if you take as a column vector, it should be, yeah, one bit. If you take beta as a column vector, then n rows one column. But anyway, that won't help. Anyway, suppose you have this. That can be B. Ah, that's the mistake we were doing. Yes. So A times beta. So A is not this guy. A is this. Beta is this. Yeah, I think like we named it incorrectly. Okay. Raise hand like this. Okay. So now it is coming to picture. Y cap is equal to A into beta. Sorry, like I was confused what to name as A, beta, sorry, because beta and we are writing alphas. That was a bit of confusion in notice. Fine. So it's all good. Okay. So if we do in this format, you can actually write y cap equals to A into beta. Fine. All good. So now you know that the data set we wrote, if we have, what's the point now? If we have how many points? Xi to yi, how many points? I equal to 1 to m number of data points, and how many basis functions? F1 to Fn. This number of basis functions, and we want to estimate the value of y at these values. Okay, estimate. So we can write it in terms of matrix. How we can write in terms of matrix? Y cap equals to A into beta, where A is the function of parameter values, and beta is what we want to find. Our aim is to find beta, because A we know, y cap we will see, y cap we will have. So how to find beta? Okay. Basically, this can be seen in terms of graph actually. So you can see, suppose we have this xy plane, and it is some important concept also. So suppose this is our estimation curve. This is our estimation curve, that is y cap equals to A beta. You can write it in terms of y equal to w naught plus w1 x in order to visualize here. Okay. And this is our y. Okay. And of course, our regression line will miss some points. That is the point. Okay. What is our aim? Our aim is to minimize what? Our aim is to minimize the distance between this. Our aim is to minimize the distance between this. And when the distance can be minimized, you can take, I will ask you one question. You have a choice. Which one you take to minimize the distance? The blue one, CN1, or the red one? Think a bit. You cannot take the CN one, because CN, the red one is the perpendicular one. The red one is the perpendicular distance between y and y cap equals to A beta. So perpendicular distance, what is the least distance from a point to a line. If you have a point, and if you have a straight line, what is the minimum distance between the point and the straight line? The perpendicular distance. The perpendicular distance is the only minimum distance between the curve. Any other distance you take, it will be greater than L1, L2. L1 will be greater than L2. So therefore, in order to minimize the error, you have to take which one, blue or the red? The red is the perpendicular distance. So red curve, if you take, that will be the minimum distance. Okay. So that will, but this minimum distance is equal to, in terms of vector. In terms of vector, can you write? Can you write this in terms of vector notation? So you now know that this is our desired line. Now this is one vector, this is another vector. Can we get this vector? You know the rule of vectors, vector addition. What should this be? This is the resultant, kind of, you can think. So from vector law of addition, you can write y cap plus r cap equals to, sorry, no, why I am using caps. Only y hat will be used. Yes, this is the relation. Y hat, this vector plus this vector is equal to the resultant. Okay, so what should be the resultant vector? Y minus y cap. So r is equal to this resultant vector is nothing but y minus y cap. And our aim is to minimize that length of that vector. Understood? Our aim is to minimize y minus y cap mod, the length of that vector. You got the idea? What does it mean? So that is like, you can say total squared error, E, is nothing but norm of y minus y cap, and you square it. Second norm. What is the second norm? Norm 2, root over of that. Root over x2 minus x1 squared plus that. Euclidean norm, normal Euclidean norm. Okay. And we are squaring it because you know, if this is the regression line, some point is here, some point is here of equal distance, then here it will give you the positive one, here it will give you the negative one. When you take only, instead of square, you take just sum plus minus, there is a chance that they might cancel out, give you zero error, where it is not the case. Therefore, if you square each of them, you avoid it. It's a normal technique in statistics, isn't it? Normal technique in statistics. If you have error, you normally square it and add. Okay. Y minus y cap. Okay. So our aim is to, what is our aim? To y and y cap as close as possible. For us, y and y cap should be as close as possible. Y cap is the predicted one. Y is given to you. Prediction and the actual should be as close as possible. That's our aim. So our aim is to minimize E. Our aim is to minimize E. Our aim is to minimize E. Okay. Okay. So it should be perpendicular. So what we got, in order to make this as close as possible, y minus y cap should be what? Perpendicular. Should be perpendicular to careful. There is y and y cap. Two things are there. Y and y cap. Y is the actual data. Y cap is the estimated one. So it should be perpendicular to what? Y cap. It should be perpendicular to y cap. Now what should I take? Now it is very tempting for me to take the dot product, isn't it? If two vectors are perpendicular, what should be their dot product? Huh? X, y, dot product is mod x mod y cos theta, right? If it is perpendicular, cos 90 is 0. Okay. These things you should exercise your mind regularly. Okay. Fine. So I will do you one trick about the dot product. Take two vectors. Here I am discussing a bit of preliminary of dot product. Okay. Take two vectors. Let v comma w in Rn. They are in Rn vectors, n number of tuples. You want to take the dot product, v dot w. Okay. So suppose v is some v1, v2 up to vn are. So what you will get? You will get v1 w1 plus v2 w2 so on vn w1. Is that correct? Fine. What is v? I told you. Okay. Now, what is V transpose times W? This matrix multiplication. V transpose is V1 up to Vn. This is n rows, one column. W is W1, Wn. What is this? 1 into n columns. Matrix multiplication is possible. Okay. So what should I get here? Okay. So can you see, can you feel, or should I do the other way around? I need a 1 cross 1. I need a 1 cross 1. For 1 cross 1, what I should do? Actually, you can write this dot product as V transpose W actually. But then why are we not getting? Okay, I think today we are playing with matrices. How about this one? Suppose V was a column vector and W was a row vector. Okay. So if V transpose W, you do, what you get? Correct. Now you will get 1 cross 1. So can you see that V dot W is nothing but V transpose W? The dot product is nothing but multiplying the transpose of the vector times W. Okay. The same thing we will use here. Same thing we will use here. That implies y minus y cap should be perpendicular to y cap. What does it mean? The dot product of y minus y cap with y cap should be 0. The dot product should be 0, isn't it? Okay. Now this dot product is 0 means y cap transpose times y minus y cap should also be 0. I'm just using the technique from this side note. Y cap transpose times y minus y cap should be 0. Agree? But what we have, what is y cap? A into beta. Y cap is A into beta, right? Y cap is A into beta, is it? Are you getting it? So here you will see regression. Regression is another version you are getting will be notation. You will be working with lot of notation. Y cap, X star, all these things. Y bar, XY whole bar, X bar into Y bar, all these things. In regression, it is very easier, but notations you have to understand. What is Y cap? What is Y? Okay. Anyway, you already know Y cap is the estimation function, and our aim is to find beta. That's what we are doing all these calculations. Our aim is to find beta, right? So now can we find the beta? So can you substitute Y cap here in this equation? Can you substitute? And what you will get? Substitute and let me know. Can you substitute? Try to do. So what you have to do? A beta transpose times something. So can you do? And I told you our aim is to find beta. Can we find beta using this? Let me know. Yeah. What we should do? A beta transpose, right? Minus y minus a beta equal to 0. So this is beta transpose a transpose y minus beta transpose a beta equal to 0. So I'm seeing lot of beta transpose. So what I will do, I will take beta transpose to be common. A transpose y minus A transpose A beta equal to 0. Through this, what I'm getting, beta transpose of course won't be equal to 0 because beta is the set of unknowns we have to find, the coefficients. So therefore, what other can be 0? A transpose, since beta equal to 0 is a trivial solution. So we don't want it. If we beta equal to 0, why we'll do so much calculation? So beta is not 0. So what other can be 0? This implies A transpose y minus A transpose A beta should be 0. Okay. Now, can we find something beta here? So beta should be equal to A transpose A whole inverse times A transpose y. Is it okay? Is it okay? So solving for beta, this beta will give you least square regression actually. Okay. But what is this beta equal to A transpose A inverse A transpose y? It's very complicated matrix looking equation. What is? Y is already being given to you. A transpose A, all this you can compute. But this A transpose A inverse into A is something special. This A transpose A inverse A transpose is known as pseudo inverse. Okay, is known as pseudo inverse of A. It is something very nice. Okay, so it tells you that if you want to find a lot of like data sets you have, a lot of unknowns, alpha 1, alpha 2 up to alpha n. And if you want to find, pack them into matrices, apply the pseudo inverse. Okay, and it will give you the set of unknowns to fit the regression line. That's it. That is it. Okay. So this guy, of course, is a bit difficult to A transpose A, and you have to take the inverse of such big matrices and you have to multiply with it, A transpose. So I will show you that this is being taken care of in Python by PINV function. If you just give matrix A, PINV A, the output will be A transpose A inverse A transpose. It will compute that, okay, in Python. So this is something very nice, and it is something known as like generalized inverse. Okay, Penrose generalized inverse of A. Okay, so that's the part, and yeah, that is it. Like maybe I can show you some Python code related to this. So you understood like how we came across to find beta, how we found beta. What we did, I will just go through this a bit soon. So I told you that suppose we have this set of data. Okay, suppose you have this set of data at m points. What does this mean? M data points. M data points, n basis functions. If you have this data set with you, then how to proceed with this? Okay, what we are doing, nothing more. We are just packaging the data in matrices. We packaged y cap into y. We packaged alpha i's into beta, and f1, f2 up to so on, all these things into A. And then we wrote this in all this equation set of system of equations into y cap equals to A beta. Okay. Then what we did, nothing, like we just introduced this graphical approach that y cap equals to A beta is this line here, 1, and y is the original solution 2. Now we want our regression line as close as to the original data. That means y cap should be as close as y. When that is possible, if you take a perpendicular distance between them, a perpendicular line. Any other line will have a greater distance between them. Okay. So how it is that possible? Y cap should be perpendicular to Y. If Y cap is perpendicular to Y, what does it mean? This Y minus Y cap dot product of Y cap is 0. The dot product can be written as V transpose W. V dot W is nothing but V transpose W. So we wrote in transpose form. Okay. But remember that Y cap is A beta already. That's what we did in matrix multiplication. Now you just have to put that and solve it. Okay. If you put that, then yeah, you have to solve this matrix a bit. But when you write beta in terms of A, okay, you get this equation. Beta equals to the generalized inverse times Y. What is the Murray-Penrose inverse? A transpose A whole inverse A transpose. Okay, that is the generalized Murray-Penrose inverse. Okay, so using this idea, you can find the beta, and though that beta will be best beta because that will ensure the minimal distance between the the estimated or predicted and the actual data set. Okay, so you saw how this is being used. Okay, let us come to this Murray-Penrose generalized inverse in Python. Okay, so what I am doing is I am given this A vector here. Okay, you can see, and I am given this B vector here. Okay, what I am doing here is nothing. np.lin alg. You saw this in the last semester. Then inf. This is the very crude way of doing things. This is very crude way. A transpose A, and then I am taking the inverse, multiplying with A transpose. Okay, and I am getting the pseudo inverse. But that is very hard, right? That is very hard. How can we do this in other way? NumPy. NumPy provides us with a function for computing the pseudo inverse, PINV. PINV, if you use, it will do it for you. So PINV A, that's it. You just have to note what is A, what is B, and you know pseudo inverse of A times B you have to do. Okay, and that is it. Pseudo inverse of A, B. Finish. The same answer you are getting in both the cases. You can see minus 1.4, minus 1.4. Okay, so you can do either way. So I suggest you do use PINV function in Python to compute the pseudo inverse. Okay. Anyway, so maybe next class we can see this. Yeah. Yeah. Can we, so let us consider this artificial data we have. Can we consider this artificial data? Read this question carefully. Read this question carefully. Read this question carefully. What you have. So I'm trying to do a least square regression here. I'm trying to do a least square regression. So for that, I am defining my X data set in between 0 to 1. You can see the number of data points. And then I'm defining Y. I am adding some randomness in my data. How am I adding randomness in my data? You can see 1 plus X. That means I want linear distribution, linear, not any nonlinear things, but I am adding some randomness to it. So therefore, you can see 1 plus X, if I write, it will be just 1 plus X, a straight line. Instead, it will be some randomness distributed throughout. So you can see that in blue, like you can see that. But it should give you an idea of a straight line. So it is just like this. It should be the straight line. But since we are adding that random, due to this point gets shifted somewhere here, like this. And that's what you actually see here. Okay. That's how the randomness brings to picture. And I want to use least square regression here. Fine. So here I have defined the function, you can see. Okay, fine. Then I'm using the, what do you call that? Yes, the generalized inverse. A transpose A, whole inverse A transpose. A transpose A, inverse, then multiplying with A transpose, dot product. This line, try to see, does this line tell you this? Does this line exactly tell you this, that line where my cursor is? Does it tell? No. How many you think it tells? Tells. It tells. Okay. So that you see the theta, these are the coefficient W0, W1. W0, W1. And that you are plotting in red line. Okay, I suggest you can compute the R2 for this case. And I don't think R2 will be that good. I don't think R2 will be that good because you are missing a lot of below points. Okay. R2 will be maybe very close here. Okay. Fine. So I told you, yeah, pseudo inverse. Yes, and even if you don't need to understand all this math, you can just like use NumPy from the linear algebra package. You can see NumPy has already implemented the least square method that we can call the function to get a solution. But you need the left hand side, you need the right hand side. That's it. The number of unknowns will be computed by itself. Okay. So A and Y you just give it as input LSTSQ. LSTSQ. What does it mean? Yes, that function, if you just call it, and it will just give you the coefficient, unknown coefficient of the line. What is the slope? What is the W0? What is the W1 for that line? You can see that happening here. np.lin.alg.lstsq, you are giving that A and Y. This is by default R, C, O, and D, none. If you want some speciality, you can add something here. I suggest you go into that manual. Go into manual of LSTSQ. So I suggest whatever you are learning here, try to write. PINV you learned. What you learned using Python here in this class? Pseudo inverse. LSTSQ. Then anything else? Anything else I covered? I don't think so. Yeah, that is it, I think. Yeah. Fine. Yeah, optimize.curve fit. Eh? Something. Optimize.curve fit. Optimize.curve fit. That is another way. Here you are optimizing your data and the regression line. Okay. So you can see this is the random set of data, and you are trying to define that linear relationship, that is y equal to ax plus b. Okay. Y equals to ax plus b. Fine. Then theta is equal to optimize.curve fit func and this data set. Then it is giving you the what do you call W0 and W1. Fine. So this is all. Next class we will try to learn something about least square regression for nonlinear functions. Least square regression for nonlinear function. There you will see how you can convert nonlinear functions in terms of least square regression using log or any other functions here. You can see this is the data, how we are going to fit it. Okay, how we are going to fit it. And then we will see some polynomial regression, and I will show you how we can use different order of polynomials to fit the data. Okay, you can see that. And how we can use this optimize.curve fit function from SciPy to fit. Actually, you will get the same. And yeah, that is it. So with that, maybe next class we can start.